When you connect a laptop or a phone to a network, you don't track down the system administrator to manually type in an IP address, a subnet mask, and a default gateway. Instead, modern networks use DHCP to assign those configurations dynamically. This diagram shows exactly how that automatic assignment happens using the four-step DORA process. It starts when a client sends a discover message, a server replies with an offer, the client responds with a request, and the server finalizes it with an acknowledge. But look at the top discover row of this sequence table. The client has to send this initial message as a network broadcast because it doesn't know where the server is. By default, routers are strictly designed to block broadcasts from leaving the local subnet. Here is our topology map with three distinct nodes: SRv1 on the left as our central DHCP server, R1 in the middle as our router, and PC1 on the right as a client. We must configure this so PC1's broadcast reaches SRv1 across the router. A basic home router just acts as a local DHCP server for a single network. Overriding this router broadcast boundary is the technique that allows a single, centralized server to handle IP assignments for hundreds of subnets across an entire organization. We begin our configuration by logging into the global configuration mode of our primary server router. Looking at the configuration output, the critical first command we execute is IP DHCP excluded address. We establish a range of addresses to exclude before we build any distribution pools. If you fail to set these exclusions first, the server might immediately assign an address that already belongs to a critical piece of hardware, like a switch or a default gateway. That creates an IP conflict and will instantly drop devices from the local network. With static IPs protected, we create a named pool using the IP DHCP pool command, then define the target network block. We also specify the DNS server and default gateway directly within this same configuration block. Centralizing these parameters into a single server means network administrators can update routing protocols or DNS settings across an entire enterprise instantly without logging into a single end-user workstation. Next, we move to the intermediary router. Right now, this router serves as a dead end where the local broadcast messages from the client are dropped. This diagram illustrates the fix. We configure the router as a DHCP relay agent, which intercepts the local broadcast destination, the 255 address, and repacks it into a targeted unicast destination aimed directly at the server. To set this up, we look at the command line for our intermediary router and enter the interface configuration mode. The most common configuration error here is applying this to the wrong port. The configuration must be applied to the interface facing the client, not the server, because that is where the broadcast physically hits the router. On that client-facing interface, we type IP helper address, followed by the IP of our remote DHCP server. Running a show command verifies our work, and the output confirms the helper address is active. Deploying these relay agents allow large organizations to run one secure, centralized server, rather than placing independent DHCP servers into every single building or department. We turn our attention to the final component, the remote client device, which currently lacks any IP configuration. Looking at the terminal output for the client router interface, we run a single command, IP address DHCP. This forces the interface to request its IP dynamically from the network. As always, when setting up a new connection, ensure the physical port is turned on using the standard no shutdown command. We wait a few seconds, and the system log updates. The output displays address determined by DHCP, proving the client successfully pulled an IP from the central pool. To verify this on a Windows machine instead of a Cisco router, open the command prompt and type ipconfig/release, followed by ipconfig/renew. The arrival of a valid IP address on the client proves the relay architecture works, successfully bridging the subnets and defeating the broadcast boundary. The complete architecture is now online. The dynamic client broadcasts its request, the intermediary bridge repacks it for transit, and the central authority delivers the lease. Once a dynamic network like this has been running for a while, keeping track of exactly which piece of physical hardware currently holds which IP address becomes an administrative challenge. To audit the network, you use the show IP DHCP binding command on the central server. This provides a complete log, matching every active leased IP address directly to its corresponding client hardware MAC address. Mastering the deployment of relay agents and central pools takes a rigid manual infrastructure, and turns it into a fluid enterprise network that largely manages itself.